I will be presenting to you on my thesis work on approximate methods for validating autonomous systems in simulation. So as an overview of what we'll be talking about today, we'll start with an introduction where I'll go over some motivation and background information. I'll talk about adaptive stress testing, which is the method that all of my contributions sort of contribute towards. And then we'll go over the sort of 4 categories of my contributions: scalability, hard exploration, high fidelity, and the AST Toolbox. Unfortunately, I don't have time to go really in depth onto all 4 of those contributions. So I'm going to skim over 3 of those, and then we'll really do a deeper dive into the high fidelity contribution. And then finally, at the end, have a few acknowledgements to make, and then we'll finish, if we have time, with some Q&A. So let's start with some motivation. This slide's interesting because I actually made this slide 3 years ago for my quals research presentation. And the articles that I clipped here are still sadly relevant today. You know, back in 2016, 2017, we heard a lot of promises of autonomous driving in 2020, 2021, or even sooner than that. And all these articles were saying, you know, it's right around the corner. But today, we're still seeing those same articles. Autonomous driving is right around the corner. So the question becomes, why has so little changed in this industry in the last few years? And I would contend that the reason comes down to the idea of creating safe systems versus validating safe systems. So there's tons of autonomous systems emerging into the world today. A few, for example, I have an app that has an AI coach to give me different fitness results. There's quadcopter delivery drones. There's robots that are going to be delivering food. And there's a lot of industry effort on how do we make these systems perform better? How do we actually create the systems? However, there's less industry focus on how we actually validate these systems, which is to say, how do we prove that they do what we think they do and what we want them to do? And this is a problem because validation, as it turns out, is really hard. As an example, let's talk about autonomous vehicles. So there was a paper in 2016 that showed that safety validation of autonomous vehicles through on-road testing is pretty much impossible. We would need to have a fleet of cars drive 5 billion miles before we could have some sort of proof that they're as safe as, say, the commercial airline industry. So to get around this, we can use simulation, but that's not so straightforward either. We need high accuracy simulators to be able to have confidence in our results, but these simulators become computationally complex, and that can make validation problems intractable. So an approach that you often see in industry would be to make some sort of aggressive constraints or simplifications of the problem in an effort to make the problem smaller, and therefore we can run it. But the problem is these simplifications come at the expense of safety. So as an alternative, what we really need is to use approximate methods to allow for all the variability within these scenarios, but to still be able to solve them in a tractable way. And so that's where my 4 contributions that I'll talk about today come in. And I sort of have broken them down in 4 categories here. The first is scalability. So I'll go over a deep reinforcement learning approach to AST that is shown to have better performance and scalability than previous approaches. We'll talk about hard exploration, a type of problem where it's very difficult for reinforcement learning to work. And we'll talk about an algorithm I proposed based on GoExplore that allow us to do validation when we have these sorts of hard exploration environments. We'll talk about high fidelity. As I talked about, we need these really accurate, very expensive simulators to be confident in our results. And I'll talk about how we made some changes to AST to actually be able to use it in high fidelity. And then finally, I'll talk about the AST Toolbox, which is an open source Python package that I created that allows designers to easily apply adaptive stress testing to their own system. Throughout this presentation, we'll also keep coming back to sort of this running example of a crosswalk. So this is sort of a basic test scenario for an autonomous vehicle. So our ego vehicle, which is the vehicle we're testing, is approaching a crosswalk where a pedestrian is trying to cross, and the perception isn't perfect. So there's some sort of errors or noise in the perception. So where the pedestrian is and where the car thinks the pedestrian is may not be the same. So the naive approach, as I said, might be to make a simplification. So we can say the pedestrian is going to cross in a straight line. We can take some range of velocities and sort of test it for all the different velocities and say, well, if it's too slow or too fast, we're unsafe, but in this Goldilocks region, we're safe. Maybe that's good, maybe that's not good enough, so on and so forth. The problem is that's just too restrictive of a simplification. If you think about a pedestrian can really move in any direction across this street or away from the street. And I think anyone who's done any sort of driving can tell you pedestrians often do move in very unusual and unpredictable ways. And all it takes is one pedestrian moving in a strange way one time to create an accident that we really want to avoid. So the question is, how can we avoid having to make this implication, but still allow this sort of validation to be a tractable problem? So we'll take a step back and talk about first black box validation in general. So when we're talking about this sort of black box validation approach, we have some sort of model of our system that's acting in an environment. Now this is within simulation. So the system takes actions and then gets observations back from the environment, and based on those observations takes the next action, and so on and so forth. But then what we're also going to do is we're going to have an adversary. And this adversary tries to force the system to fail by controlling the environment using what we term disturbances. Now, disturbances is a very general term. For example, in a crosswalk scenario, a disturbance could be controlling how the pedestrian moves across the crosswalk. It could be controlling the noise on the perception system's measurements of where the pedestrian is. So disturbances is really just a general term for anything the adversary is controlling to try and force failures within our simulation loop here. And so what we're going to talk about then is a method called adaptive stress testing, which is a specific type of black box validation method. So within adaptive stress testing, this is sort of we'll do a quick mathematical background here. The idea is we're given some sort of simulator, and we want to find failures within the simulator. So we have a subset of the state space of the simulator, and the idea being, for example, where the XY location of the pedestrian and the car overlap. So therefore the cars hit the pedestrian. So that's sort of our subset of the state space that is a collision. And the idea is we want to solve this optimization problem, which is saying that we want to maximize the probability of a trajectory subject to the last state of the trajectory being in that subset, which is really just saying we want to find the most likely failure within our space of possible scenarios here, or possible scenario rollouts, really. So the way we're going to approach this is to formulate it as a Markov decision process. A lot of the people from the lab will be very familiar with MDPs, but for those who aren't, really the reason we do this is just so that we can solve it using standard reinforcement learning techniques. There's a lot of research already into how to do reinforcement learning intelligently and efficiently, and so we can use a lot of that research on our problem by formulating it as an MDP. So from a more methodology standpoint, here's how the approach works. So as I mentioned, the goal is to force failures by letting an adversarial reinforcement learner interact with the simulator. And that's the key. In this case now, our adversary that I talked about is actually represented by a reinforcement learning policy. So that policy at each time step is going to output some disturbance X to control the simulator. So that's going to go into the simulator, which is then going to update a time step or maybe update the full simulation, depending on how you run it. And then it's going to output two things, some sort of event indicator E, and then some simulation information. The event indicator just tells us, did we find a failure? Did we reach the end of our trajectory, or are we still moving? And the simulation information varies a ton based on application, but really that's just whatever information you need to also create the reward function. And we'll talk about the reward function in a second here. So the information goes to the reward function. We calculate a reward. That's sort of a numerical score. So for those people not familiar with reinforcement learning, you can think of this as sort of a video game. So each rollout is playing the game once. And so maybe you play the game and you get a score, and then you play the game a different way and you get a different score, and it's a much higher score. So any human would then say, well, that was probably the better way to play it. I'm gonna try and play it more like that way. And maybe sometimes you explore and try different strategies, and maybe sometimes you exploit and try to really focus in on the good strategies you found. So the idea here is sort of the same thing. Instead of a human, we have this machine learning algorithm and this reinforcement learning agent. But in a similar way, it's just taking these numerical scores and trying to find the best way to force failures. And what's interesting about that, as I mentioned, is sort of this black box approach. You'll notice that while there are exceptions to this, we don't really need any access to the simulator's state, for example. We don't need to be able to take gradients between simulation steps or anything like that. We sort of just treat it as a complete black box. We throw some input in, it rattles around, and then we get some output out that we use to create a reward. Then we throw some different input in, and if the reward's higher, we throw more input like that. And if the reward's lower, we go back to what we were already doing. So in this way, we're able to test systems without having any access to the internal state. Now the real, I would say, power behind this method comes from the reward function. So there's basically three cases within this reward function. The first is that the state is in our event subset, which means we found a failure. So the trajectory is over and we give a positive reward. Similarly, we are not in a failure state, but we're also at the end of our trajectory. We've hit our max time step. So that means our trajectory didn't end in failure. That's what we don't want to happen. And so we get a large negative penalty. And then finally, basically every other state in a trajectory will be this case, which is it's not the end of the trajectory and it's not in a failure state. So we're still ongoing. And at this point, what we're going to give is a penalty proportional to the log likelihood of disturbance. So really, to step away from the math for a second, what this says is because we're under this optimization problem, as we sum the log likelihood of the rewards, we're still proportional to multiplying the probability of the disturbance at each time step. So the takeaway here is that the likelier your trajectory, the higher your reward, and the less likely your trajectory, the lower your reward. So the idea would be you're going to want to find failures because you want to get that positive reward instead of that negative penalty. But between two failures, you're going to get a better reward for the likelier failure. And so in this way, the best way to maximize the score of this game, according to this reward function, is to find the likeliest failure within our possible trajectories. I did ignore this term. This is basically sort of an added heuristic. We'll talk about that a little bit in the hard exploration problem, so you can ignore this, but did want to point out that there is sort of room to add heuristics to this reward function as well. So AST has already been shown to be successful on many different problems, but especially a few years ago, there were still some outstanding issues with the method that I wanted to address. So from a scalability standpoint, we need this to work with high dimensional state and action spaces, and we want it to be able to generalize across initial conditions of a scenario. From an exploration standpoint, we don't want to have to use that heuristic reward. We allow for it, but we may not always be able to use it. So we want to make sure we can work without a heuristic reward. When we're working with high fidelity simulators, we want to be able to, we want to be sure we can run in a small enough number of iterations that we can actually afford to run in high fidelity. And finally, we want to make sure that this is an accessible method. We want people and companies to be able to use this method to validate their own autonomous systems. And so these four outstanding problems are the four categories that my contributions are sort of divided into. So for the rest of this presentation then, we'll be going over the four contribution categories within my thesis. So let's start with the scalability category. So there were sort of two separate problems here from a scalability standpoint. We had this algorithm Monte Carlo tree search working with adaptive stress testing, but there were some doubts about how well MCTS would scale to larger and harder problems. MCTS in particular has excellent exploration, but doesn't always have great exploitation. So it can find failures well, but it may not find likelier failures once it's finding failures. Deep reinforcement learning, on the other hand, is a type of sort of reinforcement learning approach that had been shown to perform well on hard high-dimensional problems already, such as Atari games. And because it has sort of less structure in its training algorithm, it's been shown to have better exploitation on a lot of problems. So on the other hand, while it may not find failures as quickly, once it finds those, it can really optimize to find the likeliest failure quite well. But there's also a second problem, which is what if we're interested in two very similar scenarios, which is often the case. So in our crosswalk example, what if we're interested in the pedestrian being 2 meters back from the crosswalk versus 3 meters back from the crosswalk? From sort of a common sense standpoint, you can see that those solutions should be pretty similar, and we should be able to use information from one to know how to sort of force a failure in the other. But the way the algorithm was designed right now was that we'd have to sort of run AST from scratch, completely new for every single one of these initial conditions, even if they're very similar. But the goal would be to instead modify it so that we can run AST once across all of these initial conditions, and therefore be much more efficient in finding our failures across a space of similar scenarios. So the solution was a new architecture with this new deep reinforcement learning algorithm. So what we did is we used a recurrent neural network. So RNNs are different from standard vanilla deep reinforcement learning in that they don't just map an input to an output. They map both an input and a previous hidden state, it's called, to an output and the next hidden state. So if you're not familiar, you can kind of think of this as someone taking notes, if you will. So they get an input and they get the notes that they took last time. And they look at that input in their notes and they say, oh, this is what I know about, this is what I'm supposed to do. And then they give the output, but then they also update their notes. And so the next time they get a new input and now they get their updated notes, give the output, update the notes again, so on and so forth. And so in this way, the recurrent neural network sort of keeps a hidden state that has latent information it can use to learn different mappings from input to output based on different areas within a trajectory. This is important because what allowed us to do is keep the black box assumption without needing access to simulation state. So our input at each time step is now purely the previous action we took, as well as the initial condition we started from. So by basing it on previous actions, we allow the hidden state to essentially store some latent information, so it learns some approximation or latent approximation of the simulator state so that it doesn't actually need to see the simulator state itself, therefore preserving the black box assumption. But the question then becomes, if we have two identical trajectories from an action standpoint, so we take the same actions, but we start from different locations, obviously those will have different results. So to be able to differentiate those, we also needed to give it the initial condition. So what this allows us to do then is each rollout, we sample an initial condition from our scenario space. And then over time, as it's training, it learns to generalize across all these initial conditions in one run instead of having to run an individual AST run for each initial condition. So what were the results here? We found that our deep reinforced learning solver outperformed Monte Carlo tree search. It found likelier failures and it found them much faster. And for the generalization work, we had great results. We found better average rewards, better maximum rewards. We found a higher percentage of collisions across our runs. And on top of that, we also got significant speed improvements. So to sort of sum up the scalability standpoint, by adding this new deep reinforcement learning architecture, we're able to create a new validation approach that had much better scalability to these high dimensional continuous state and action spaces that we see with complicated autonomous systems. And we were also able to create a system that doesn't need to be run for each individual initial condition, but instead sort of take a class of scenarios and generalize across that entire class. So now let's move on to the next contribution, which is hard exploration. So to talk about hard exploration, we should start by talking about what a heuristic reward is. I did mention these a bit earlier. And so now we'll define these. Heuristic rewards are rewards that use domain-specific knowledge to guide learning agents to better solutions. So basically, we're taking expert knowledge and we're using that to give our agent some extra information so that it knows how to find failures. So why is this important? On the screen on the right, you'll see the first screen of an Atari game called Montezuma's Revenge, which is sort of a famous benchmark for hard exploration problems. And the reason that's so hard for agents is because you have to take a lot of precise actions in the correct order before you can ever get a reward, which means for these learning algorithms, they have to sort of accidentally guess the correct sequences of actions to ever get some feedback that they're doing something right. So if you look, the Montezuma on the first level, you have to go down the ladder, jump on the rope, jump to the other platform, down the ladder, across the ground, jump over the skull, but only when it's in the direct middle of the screen. Back to the ladder, up the next one, and then you get the key. And that's when you get your first reward. So if an agent were to go down the ladder, jump on the rope, jump onto the next platform, but then jump back and hit the ground, they got no reward. So even though they took 3 of those steps correctly, they have no feedback telling them that they got halfway there. So the way we treat this is with heuristic rewards. We might use some expert knowledge to give it some reward so it knows it did a good job to get to 3 and it'll keep doing that. And then hopefully accidentally learn how to get to 4, 5, 6, 7, and then eventually the key. The problem is these heuristic rewards are difficult or undesirable to craft in a lot of cases because they require expert knowledge. And when we don't have them, we're in what we term a hard exploration problem. So because we have to take so many steps until we get our first reward, if we don't have these heuristic rewards, it becomes hard exploration. So there's a method called Go Explore. It's sort of the state-of-the-art algorithm for hard exploration problems. It set records on Montezuma's Revenge a couple years ago. And we sort of divide into 2 phases. The first phase is a biased tree search. So it's a random search that as it explores, every time it sees a new state, it stores it in a sort of a tree. And these cells are ranked according to sort of how promising they are. So in Montezuma's Revenge, the higher the score is or the further level you've reached, the more likely that you are to sample that to start a rollout again. And so each rollout samples from this tree and it samples the better states more often. And so over time, it builds up a trajectory that is sort of your best solution to a problem. But the thing is, a lot of times we don't want just a trajectory, we want a policy. So the next phase is the robustification phase, where we use the best trajectory from phase one with a learning from demonstration algorithm, which is an algorithm that takes in an expert demonstration and uses that to efficiently learn some sort of deep neural network or reinforcement learning policy. And so in this case, GoExplore uses an existing algorithm called the backward algorithm to do this robustification. So for our purposes, what we realized are both of these phases of GoExplore have different applications to our validation problem. We can use this biased tree search phase to explore a hard exploration validation approach where we don't have these heuristic rewards to help guide our adversary to failures. But then we also can use the robustification approach for any of our existing solvers. Our deep reinforcement learning, our Monte Carlo tree search, or our GoExplore solver, all three of those could potentially benefit from having this robustification phase run on the best failure they find afterwards. And so those were the approaches we took, and sort of these were our results. We created a long horizon version of our crosswalk problem where we had no heuristic rewards. And on that problem, neither deep reinforcement learning or Monte Carlo tree search could find failures. However, the GoExplore tree search phase was still able to find failures. And from the robustification standpoint, for all three solvers, the backward algorithm was able to significantly improve the results of the failures found from the previous solvers. And in fact, after running robustification, the deep reinforced learning and Monte Carlo tree search solvers were able to find nearly optimal solutions to the problems we put in front of it. So that was really encouraging. And then we can sort of sum up the takeaway from this phase is that, again, we were able to add a new approach to solving AST that allows us to work in these specific scenarios where we don't have heuristics. But we also added this general robustification phase, which allows us with any of our solvers to converge to more consistent and more likely failures, so long as you sort of have room to do that added extra compute of a robustification step afterwards. So now let's move on to sort of the deep dive of high fidelity. So I talked about high fidelity simulators earlier. The truth is there's really no hard definition of what constitutes a high fidelity versus a medium versus a low fidelity simulator. It's kind of like the famous Supreme Court case. You'll know it when you see it. But in general, we're talking about simulators that include advanced dynamic models, simulated perception from graphics, which means they take in simulation input and use that to actually run their perception models, and then full stack software and loop capabilities. So we're not just running some sort of downsized model or approximation of our autonomous system. We're actually running our full autonomous system stack within the simulator. So obviously this gives us great accuracy benefits, but the problem is they're also slow and expensive to run. So obviously, I've talked about scalability already. So, shouldn't we have already solved this problem? Unfortunately, while we did make the problems more scalable, reinforcement learning still can require thousands or tens of thousands of iterations. And that's just too many to run in high fidelity. It's just too slow, too expensive. So we need to take a different approach. So the approach we sort of thought of here is, what if we run in low fidelity first? What if we take that cheap, fast, low fidelity simulator and do the bulk of our learning there, and then use those results and transfer to high fidelity in some way. And hopefully that'll let us run much fewer high fidelity simulation steps than if we had just run from scratch in high fidelity. And the way we're going to do this is by using the backward algorithm. So the backward algorithm, I did mention earlier because it was the algorithm used by GoExplore for the robustification phase. And so we're going to take a second here and sort of dive into what the backward algorithm is and why it works so well here. And to do that, we're going to talk about what's known as the blind cliff problem. So if you've ever seen the third Indiana Jones, there's a scene in there where he has to sort of take a leap of faith and walk across this invisible bridge to get to the Holy Grail. But because he can't see the bridge, every step is sort of a guess. If he steps in the correct direction, he's going to continue across the bridge. But if he steps off to the wrong direction, he's going to fall off the bridge and die. That's sort of the blind cliff problem too. So the idea is you start in some initial state, and every state that you're in has two actions. One action takes you to the next state, but one action takes you off the cliff to a terminal failure state. But if you take all the correct actions in a row, you end up getting to the goal state. So that's what we want to achieve. But the idea here is then there are n non-terminal states between us and our goal. So if you think about a random exploration approach to this, then basically at each state, we're flipping a coin. There's a 50-50 shot we get to the next state. There's a 50-50 shot we fall off the cliff and die. So if we're doing some sort of random exploration during our rollouts, what are the chances that we'll actually find the goal? Because if we're doing reinforcement learning, we have to find that goal and get that positive reward before we can start optimizing to improve our policy. So if there are only 5 states between us and our goal, we have a 3% chance on each iteration of getting to the goal state just through random actions. So that means on average, we're going to take 32 iterations before we make it to our goal state. That's not bad. If there are 10 states, all right, now we're starting to hit a problem. Now we're going to take 1,000 iterations before we can make it to our goal state. And so as I was talking about, at each state, we have to flip a coin, 50-50 shot to make it here, 50-50 shot to make it here, 50-50 shot to make it here, and then to our goal. The problem is, as we scale up, we have this sort of exponential explosion in how unlikely it is to find our goal state. So with 20 states between us and our goal, it'll take over 1 million iterations on average to find a successful navigation to the goal state. And if we have 50 states between us and our goal, it's a number so big that I have no clue how to say that in English. So you can see that this especially will be a problem if we have continuous states or a higher number of states or something like that. We're really just never going to randomly find our way to this goal state on this problem. So enter the backward algorithm. The backward algorithm works by taking an expert demonstration. So we assume some expert has already solved this for us. So they've already shown us how to get from state 0 to the goal state. And what we're going to do is we're going to start training our agent from the step n-1, so the second to last state of this expert trajectory. So from this state, there are 2 actions we can take. One action takes us to terminal, and one action takes us to goal. So now instead of having a 3% chance or what have you, we have that 50-50 chance again, which means it's only going to take a few iterations for us to find our way from this state to the goal state. And then we can quickly learn a policy that tells us whenever we're in state n-1, take this action and you win. Once we've done enough training to do as well or better than the expert from state n-1, we take another step back. Now we're in state n-2. So once again, from this state, we have a 50-50 shot. Either we're at terminal or we end up in state n-1. But once we're in state n-1, we already have a trained policy that tells us how to get from here to the goal state, which means it's basically, again, a one-step 50-50 shot to get to state n-1, and then we've already won because we know how to win from here. So again, we train until we're better than the expert, and then we move back again. And we keep doing this over and over until we're training from our initial state. And even in the initial state, it's the same thing as previously. So we have a 50-50 shot of making it to state 1. But once we do, we've already trained from state 1, so we know how to get to state 2 and to state 3, and so on and so forth until we get to state n-2 to state n-1, and finally to our goal state. So this is why it's called the backward algorithm, because as you're training, you sort of sequentially step back along this expert trajectory until you train from the initial state that you're interested in. And so in this way, it sort of takes this exponential problem and instead turns it into a series of much easier problems that's only linear in your number of sort of states between you and the goal state. So why are we using the backward algorithm for our problem? Well, there's a few advantages that we have. First of all, it takes way less iterations than just running vanilla deep reinforcement learning from scratch because you have the benefit of learning from an expert. And similarly, it has that scalability. So it scales particularly well for hard exploration problems. It didn't come up in our example, but a neat aspect to the backward algorithm is it can actually improve upon the expert. So if your expert gives you a good solution, but not a perfect solution, the backward algorithm can actually find better solutions through its training. And then finally, it's cheap to reject a failure. We'll come back to that in a little bit. So the way we're going to apply this is first, we're going to find failures with AST in low fidelity, where it's cheap and fast to run. And those failures we're going to call candidate failures. And then we're going to use each of those candidate failures as the expert demonstration to the backward algorithm in high fidelity. Now, those of you who might have some experience in this field might have some sort of alarm bells going off in your head, because there's definitely some assumptions being made here that may not be fair to make. And so let's go over those a little bit. High fidelity is not a perfect representation of reality, but hopefully it's good enough that we can still use it to learn something about our system. Low fidelity, though, is also not a perfect representation of high fidelity. So what we have here is sort of a graph, sort of an imaginary area. So we imagine our x-axis is somehow some encapsulation of all our possible simulation scenarios. And then our y-axis is probability. So the higher up you are, the likelier the failure scenario, or the scenario in general. And then I outlined in red, these are the scenarios that in our high fidelity simulator end in failure. So when we add our low fidelity simulator, maybe in an ideal world, our low fidelity simulator is just a relaxation of our high fidelity simulator. And so all of our failures are encapsulated by low fidelity. This would be great. This would be what we want. Unfortunately, there's really no way to guarantee this, and not even any way to be confident that this would be the case. It probably wouldn't be. Much more likely, we're going to have some series of failures that exist in high fidelity that low fidelity doesn't cover here. So if we look at sort of what we're looking at here, these purple regions are what we'll call covered failures. So these are high fidelity failures that exist also in low fidelity. Then we have our uncovered failures. So these are the failures that exist in high fidelity. So we want to be able to find those, but unfortunately don't exist in low fidelity. The simulator, because of fidelity differences, the same inputs don't lead to those outputs. And then finally, we have what we'll call spurious failures. Which is sort of the reverse. These are failures that exist in low fidelity that don't exist in high fidelity. So these are failures that are not actually failures of our system, but instead are just failures of our simulator. So these are failures we don't care about because they don't tell us anything about our system. They're just simulator mistakes. So this is what I talked about with rejecting failures quickly. With the backward algorithm, as we saw, because of the unique way it trains, early on in training, we require less steps per sort of batch of rollouts because we're only taking 1 step or 2 step or 3 steps instead of the full 50 or 100 step trajectory. And so the way we sort of reject these spurious failures is we have a limit on how much we'll train at each step. So if at step 10, we run 10 epochs and we still haven't found a failure or a way to get back to step 9 to get to that failure, we're going to say, okay, well, this is either too hard or just a spurious failure. It doesn't exist in high fidelity, and so we're going to reject it. And because we were running the backwards algorithm, instead of having to run 100 steps for all of those 10 epochs, we're only running 9 steps or 10 steps each epoch. So that's how it's sort of cheap with the backwards algorithm to reject these spurious failures. But that's obviously not the only issue we're worried about. The other issue we're worried about is those missing uncovered failures. And so to focus in a little bit more on that, what we're really interested in because of AST is on finding the most likely failure. So the way this is drawn right now, this would be fine because the most likely failure in high fidelity also exists in low fidelity. But that doesn't need to be the case either. It's possible that our low fidelity approximation doesn't include the high fidelity most likely failure. And so that's the case here then would be that most likely failure in high fidelity is different than the most likely failure in low fidelity. So the question becomes, as we optimize to find the most likely failure in low fidelity, does that actually help us in high fidelity, or is it going to take us down a path that means we don't find failures in high fidelity, or we don't find a likely enough failure in high fidelity? How confident can we be in different cases that this sort of approach is actually going to allow us to safely validate a system, and that we're not creating blind spots that'll lead to errors in our system that we don't catch. So to sort of explore the different ways that this algorithm works, I created sort of 5 different case studies that we'll go over here. So the first is time discretization. And so each of these 5 case studies is supposed to model sort of a different way that low fidelity and high fidelity simulators might differ. So in this case, the low fidelity has a much less fine time discretization. So the low fidelity trajectory takes only 10 steps and each step is a ½ second, whereas the high fidelity simulator takes 50 steps at 0.1 seconds each. And so you can see on this table, I know the table's a little busy for everyone to really process. Thankfully, my thesis will be online, so everyone I'm sure will go later to really look in detail at these results. But one thing to pay attention to when we look at these tables is the load lo-fi policy column. An interesting thing is that because of the way the backwards algorithm works, it uses the same deep reinforcement learning architecture as running DRL from scratch. The only difference is sort of the scaffolding on how it actually runs the rollouts. So what that means is when I run deep reinforcement learning in low fidelity first, I can actually load those weights if I want to, and use those weights to initialize the backwards algorithm when I run at high fidelity. The question is that a good idea? Because we may be introducing some significant biases into our network by initializing it to this trained lo-fi policy instead of from scratch. So I ran it both ways. In one case, I'll initialize the backwards algorithm from scratch when I run high fidelity, and in the other case, I'll load those weights from low fidelity. And so in this case, the best of the two was able to find a failure in high fidelity with only 34% of the total high fidelity steps needed compared to running deep reinforcement learning from scratch in high fidelity. And both of these approaches was also able to find a failure that was actually likelier than what we found by running AST from scratch in high fidelity. So we'll move on to the next case study then, which is dynamics. So this is supposed to model the difference in sort of the accuracy of the dynamics transition models of a simulator. So in this case, the lo-fi simulator rounds all of its simulation state variables to 1 decimal point, whereas high fidelity runs with the full 32-bit floats. And in this case, we did even better. When we load the lo-fi policy, we find a failure in only 6% of the high fidelity steps needed, whereas and the reward's a little bit better. Whereas not loading the lo-fi policy, we still only take 28% of the total steps needed, but we also find a significantly likelier failure. And that's sort of an illustration of the bias I talked about. Although loading the policy allows us to work faster because we can sort of skip some of the training at the front as it already has some understanding of how to force failures, it isn't able to find as likely of a failure because some of the biases that it's learned in low fidelity may not apply, so it doesn't perform quite as well at finding a likelier failure in high fidelity. The tracker case study. So I talked about how there's noisy measurements of pedestrian location for this car. So the way we do this in high fidelity, or normally I should say, is we have sort of this alpha beta filter, which basically means it's looking at a bunch of different noisy measurements and using those all to create sort of a best guess of where the pedestrian is. So in this case study in low fidelity, we turn that off. So now at each time step, it just directly uses the noisy measurement of where the pedestrian is instead of trying to smooth out those measurements. And then high fidelity uses the tracker as normal. Once again, we were able to find a failure in only 6% of the total high fidelity steps needed. And again, both were likelier failures. And then the most in-depth case study is the perception case study. So in this case, the normal simulator is now our lo-fi simulator. And in hi-fi, we created sort of an entirely new perception system that did perception based on sort of a LiDAR model and using dynamic occupancy grids. So it's a much more advanced state-of-the-art sort of perception model. The only downside is because of this new perception model, now the size of our action space is different between low and high fidelity. So in this case, now our deep reinforcement learning architecture changes, which means I can no longer load the lo-fi policy into hi-fi. So in this case, you'll notice there's only one entry because I had to initialize the backward algorithm from scratch. There are some ideas on how to get around that, but for the purposes of the thesis in this presentation, we're not going to load the lo-fi policy here. So in this case, despite the difficulty and the sort of in-depthness of this case study, we actually had the best results of any of them. We only needed 4.7% of the total high fidelity steps to find a failure. And once again, the final reward that we found was much better than running AST from scratch in high fidelity, which, as we talked about earlier, means we're finding a likelier failure in this case. And then finally, the most exciting case study, we worked with some wonderful partners at NVIDIA to implement AST on DriveSim. So DriveSim is their actual high fidelity simulator, state-of-the-art. It has sort of all those features I talked about: high accuracy dynamics. It has perception from graphics, software loop simulation. You can see a picture there of a rendering. So it's gorgeous, state-of-the-art video game level graphics. Really impressive stuff. Because of sort of the time constraints and the complexity of the approach, I wasn't able to implement parallelization for this case study, which means unlike most approaches and unlike this would work if we actually did this for real in industry, we're not running 1,000 batches at once. I had to run these sequentially one in a row, which is obviously going to make the wall clock time significantly worse. Despite that, and despite how high fidelity this simulator is, we were still able to find a failure in only 10 hours, and that required only 4,000 steps. So that was incredibly exciting because that's sort of the final proof in the pudding, if you will, because I guess I may have buried the lead here, but the low fidelity simulator that we used for this work was my like toy simulator in Python. So it's not like it's a tuned down version of DriveSim. It's a completely separate simulator that I was able to write myself over the last couple of years. And even so, the lessons learned in that low fidelity simulator allowed us to quickly find a failure in high fidelity in the incredible NVIDIA DriveSim simulator. So sort of in conclusion, the first point to take away is that across all these case studies, the best failure found with the backward algorithm method was actually likelier than the failures found running AST from scratch. So this is really reassuring. This sort of eases the worries that these uncovered failures are going to be a significant problem for us. It appears that in all these different ways of modifying low to high fidelity, we are still able to converge to a likelier high fidelity failure. Also, which is what we wanted from the beginning, we were able to significantly reduce the number of high fidelity steps we had to run, which makes this much more tractable in high fidelity simulators. And then finally, just an interesting note, it seems like the method performed best when we had sort of changes in models. So when we had a low fidelity approximation of perception where we turned off the tracker or where we went from a basic perception model to this LiDAR model, the method was able to, in a very short number of training time or a very small number of steps, learn how to take that low fidelity failure and turn it into a high fidelity failure. So finally, let's talk about the AST Toolbox. This is honestly my favorite contribution, but it's also probably the most boring to talk about. So we'll just go through this pretty quickly. So the whole point of this is accessibility. The idea of this whole thesis is that validation is an essential step towards safe autonomy. And I was once told during an internship, a line that really stuck with me is the idea that safety should be collaborative, not competitive. We want autonomous vehicle companies to all be equally, perfectly, if possible, safe. We don't want them to be competing such that the loser of the safety competition means that we're the ones getting hurt. So to help sort of facilitate that, we want all validation methods, if possible, to be open source, readily available, and easy as possible to use. So towards that end, I created the AST Toolbox. It's an open source Python toolbox, easily applicable and extensible, and combines sort of all the research work, not just my own, but some other people's as well from the last few years, to allow anyone to sort of easily apply AST, even if they're not an expert in reinforcement learning. So, real quick, just from a design standpoint, the way this works, we have sort of an AST environment that turns the AST problem into an OpenAI gym environment. If you're familiar with reinforcement learning, you'll know that gym environments are sort of the standard on how we implement and program reinforcement learning. And the advantage of this means that there's tons of open source libraries out there to do reinforcement learning for gym environments. So there's tons of off-the-shelf options for other people who are experts in reinforcement learning to sort of have done that work for you, so you don't have to be an expert in reinforcement learning. We ourselves package the toolbox with Garage, which is sort of our favorite version of these different reinforcement learning libraries, but you could use others as well. As part of that, you have to define this AST spaces, which is just for your state and action space, you just have to give the minimum and the maximum values for each sort of number within there. So it's just a parameter range for your state and action spaces. And then finally, the other key, I did say easy as possible to implement. And so this is sort of where the difficulty is hidden. I can sit here and say, oh, well, it's easy. All you have to do is write this AST simulator class that wraps your simulator. On the one hand, that's true. What you need to do is just write this Python class that allows you to sort of step your simulator, reset your simulator, and maybe get some information from it. And the advantage of that means your simulator can be Python, but it could be C, it could be MATLAB, it could be compiled code. It doesn't matter, as long as you can sort of write this wrapper class that has this sort of few different access functions to your simulator. Of course, that's a gross simplification because as I found out working with real life high fidelity simulators, writing those access functions is not necessarily easy. It can still be a significant engineering challenge. But the key is that sort of a very solvable, straightforward engineering challenge instead of having to be a research challenge. And finally, that information is passed to your reward function, which is built the same way we talked about earlier and allows you to sort of create easily that AST reward for your own problem, potentially with heuristics. So, just as a proof of concept, we did a few different case studies, and the one I want to highlight is the automatic transmission case study. So there's a model of a 4-speed automatic transmission, and the idea is that you have two inputs, your throttle and your brake pedals, and you want to somehow force a violation of constraints of either the speed or RPM constraints on the transmission. Unlike most problems, though, it's not sort of like a real-time input-output, so you can't just toggle the pedals really quickly and hope it breaks. Instead, you get 4 inputs, and at each input, you input a throttle level, a brake level, and a time step. So essentially, you have 30 seconds, and it's a step function that steps at 4 different time steps. So you get to pick how much it steps and when those steps occur, but you're limited to 4 discrete changes. It's a very difficult problem. So first we did an easier version where we made some relaxations. And so we ran a random search baseline, and then we ran AST twice, once with the Monte Carlo tree search, the MCTS solver, and then once with deep reinforcement learning, where we did the optimization with a method called proximal policy optimization, PPO. So we compared those, and random search unable to find failures, which is not particularly surprising, but both MCTS and PPO were able to find failures on this problem. But then we went with the harder version. And so this case study actually comes from a competition for black box validation algorithms. And within this competition, I think, now I can't remember off the top of my head, but I think 1 or maybe 2 of the algorithms last time were actually able to find failures at all. Most of the algorithms just cannot find failures on this problem because it's so difficult. And that was true for our MCTS. MCTS didn't find failures here. But really excitingly, PPO for us found failures, and it found failures basically as quickly as the best algorithm from the most recent competition. And this is especially exciting because most of these other algorithms, their only goal is to find failures, where we have that added goal of finding the most likely failure. And so despite this sort of added complexity, we are still able to find failures as fast as sort of the best other algorithms out there, and then better than most of the existing solutions. So that was something I think as a team we were really proud of and really excited to see those results. So sort of in conclusion then, these were, again, the 4 categories of my contributions. We talked about scalability, we talked about hard exploration, we talked about working in high fidelity simulators, and then finally we talked about the AST Toolbox. And so I hope you'll agree with me, certainly hope the panel agrees with me, that between these 4 sort of categories of contributions, this thesis presents a significant step forward in approximate methods for validating autonomous systems. And as much as I hope the community agrees with me, more importantly, I hope industry agrees with me in the sense that I really hope these methods can someday be used on actual autonomous systems to help make them safer. That's really the goal that I want to see happen, and that would be what I would look back upon and say, okay, that was really a successful research project.